to defend the fact that MPI processes can run in shared memory, describing a lot of side effects of this layout. And to do so, I will start with some obvious observation about the boundaries in shared memory compared to between MPI processes. And then I will slowly unfold towards the idea that MPI is a special model for distributing parallel workloads because it's the embedding programming model, sort of. And this leads to the idea of the horizontalization of compute, something that we see as a potential to better program parallel machines, and particularly large nodes. And then I will conclude with a quick related work / outline of the support of MPI in shared memory and related approaches before describing a potential use of sessions for shared memory programming. So the obvious starting point, something we all know, it's about that nodes have a topology. So nodes are getting larger and larger, and it's not changing at all because we have GPUs also which have their own topology. So what we see here on the first line is 1 megabyte copies on 3 architectures. So on the left, a Grace superchip, in the center, an Ivy Bridge, and on the right, a Sapphire Rapids. And on the second line, you have 100 megabyte copies. And we all know this NUMA effect, which leads that there are preferred links between cores which reside on the same memory bank. So it's a very simple idea, but we want MPI to be able to harvest these potential performance gains by running on the right pinning and at the right position. And it's a lot of the work we try to do using programming models. It's to correctly map the compute to these boundaries constraints. Another aspect here, closer to MPI, is the performance between processes. So in MPI, you are running inside Unix processes in most of the cases. And between Unix processes, you use SHM or shared memory segment to do the transfer. So SHM is just mapping a memory region between two processes, splitting the message in small segments and sending it by copying. A more efficient manner is cross-memory attach, which is directly doing the copy in the remote virtual address space, but it supposes some translation effects. And this is exactly what we show in the diagram on the right. Left column is 1 megabyte message, right column is 200 megabyte message. First line is intra-socket, second line is inter-socket, and we have concurrent pairs doing the copies. Again, it's a relatively obvious observation. Shared memory performs better than cross-memory attach. We also have to mitigate a bit this observation is that we did not have XPMM installed in the kernel of the machines we had. So in XPMM, you could project the remote address space in your process, allowing you to have the similar performance to shared memory, except that you need to do a sort of rendezvous protocol to agree on projecting the given segment. But yet, the thing we want to outline here again is that shared memory can perform better for moving data. But yes, we have now to explain why we would like to be in shared memory. And for this, we need to look at MPI as a special kind of model impacting the computing topology. And why I think it is special, it is because it is the embedding programming model. Simply that when you launch an MPI process, you define the CPU set for the underlying model. Here in this simple example, OpenMP, and you say my OpenMP runtime will live in the CPU set of my MPI process, which is exactly an Unix process in this case. And naturally, if you map your Unix process on the full node, here with several NUMA, the OpenMP runtime will also be able to see the full node. So the pinning is inherited from MPI sort. And so is data mapping. So here on the right, I illustrate a linear segment of data. And when you program this, it will be indexed first with the MPI rank and second with the OpenMP rank, leading us to this notion of nested programming model. As such, the parallel programs are, as of now, spatialized using a nested programming model. In this simple example, I show MPI plus OpenMP. And of course, we have CUDA, which is already an important programming model now. And all this nesting leads to complexity, and this is what we try to fight with the notion we describe in shared space in the next few slides, because this nested indexing are not ideal. Why? This is the easy case, but in practice, we have GPUs, and the GPUs here you have a grasshopper are very large chips, and so large that some of their hierarchy are called clusters themselves. And you understand that nesting and feeding such large GPU is very challenging. For HPC, you may need several kernels in parallel to be able to fully exploit all these cores, these 18,000 CUDA cores, because the HPC workloads are not really as symmetrical as some array workloads. And so it's not only this, you also need the memcopy engine, or more seriously, a fully capable 72 cores in the case of the grasshopper socket. And with these cores, you also have the notion of asymmetrical hardware, where you have a big GPU in conjunction with a capable CPU, which is not only here to do CUDA memcopy, but can also do some OpenMP regions. And so this is really the challenge we are facing now with these large nodes, or large converged architecture. It's that it's very hard to light all the silicium of the machine. Why? Because looking at HPC software, they are built in an incremental manner because they are long-living applications. So they were doing MPI, they added OpenMP, and now as the machines are both expensive GPUs, you need to add some CUDA kernels or CHEM kernels, and such. You have the fork join effect, which costs a lot to parallel efficiency. I don't say it's impossible to correctly program with current abstraction. Of course, it is possible. But in practice, the nesting creates some complexity in the ability to use the machine all the time in a constant manner. And to fix this comes the idea of the horizontalization of compute. So it's a bit of a general idea, but I think it's linked to the fact of considering MPI process as something else that Unix processes, which is where I try to bring you to. So what is horizontalization of compute? Is simply saying my hardware is not symmetrical, so will be my software. And as such, you need to map your software to this differentiated hardware. So it's a very simple idea. And this leads you to MPMD program, which is the coarser-grained approach of this collab software differentiation. So here you have the session example of zero atmosphere, maybe ad hoc storage, which is in memory storage that you may address using MPI. And doing so, you start having software in collaboration and not just runtime stacking all the way down as an SPMD model. But the story goes further. If we allow ourselves to look at MPI processes a bit differently and to open MPI to new models, we can quote the well-known quote, MPI is not synchronous, but it is mostly used as such, sadly. And if we horizontalize a bit, we have the client-server model, which is closed. We also have the underutilized in HPC systolic architectures, which are allowing pipelining parallelism. And at a coarser granularity, these architectures are workflows. MPMD already described. And further down the line, you also have malleability, which is the idea of reshaping your jobs, which is a subject studied in the session working group, and also an interesting idea of invasive computing, or considering a job mapping itself over the machine over time and conquering resource and freeing them. But what does it has to do with what I was saying before about this fork join? If we look at how we do current nesting in Grasshopper again, CPU plus GPU, but it's true also with other GPU naturally, we have this alternating behavior. So on the CPU, you have MPI plus OpenMP. You may have one of a master or a single section sending a CUDA kernel to the GPU, and so you do a CUDA kernel, you do CUDA memcopies to do the layout, and you wait for the answer. So here you have the model nesting, and you need to do some transfer using CUDA or ROCm, and you need to do some other transfer using MPI. What would be ideal and what we are imagining with this horizontalization is that we could use MPI also on the GPU. Why? Because indexing would be simpler. Here we have differentiated the software in the sense that we have MPI plus OpenMP running on the CPU, and through communication / callbacks or whatever, we can send events and coordinate also with the MPI, the CUDA kernel / ROCm kernels running on the GPU. And what was previously nesting of models now become flat communication. And this is what is happening in having a unified indexing and unified addressing of such a complex hardware. It's not science fiction, because this is exactly what vendor-specific MPI implementation, such as Nickel are doing, so the collective communication library between CUDA streams. So this single indexing is happening, and this is why we think, from the point of view of our previous work, it's interesting to consider ranks in shared memory. And so, why I am speaking of all this? It's because there is previous support of shared memory in MPI. What have we seen in the past? We had first the shared memory windows, which are in MPI 3, which allow you to project a given segment of a given set of pages in multiple processes using the RDMA window abstraction. Second thing which got in also in the standard are fine points, which we are renamed to partition communications. So this approach is simply considering that the communication has several contributors, which might be threads or GPUs, and all the associated transfer optimization you can achieve thanks to this abstraction. Things which did not get in the standard also consist in endpoints. Endpoints were virtual MPI ranks, which were created inside a given rank. This is very close to the point we try to come to in this presentation. Also, the support for active messages or remote procedure call. If you look at the figure in I outlined with the GPU, RPC is like calling a function and getting its response. It's a very simple pattern. This is exactly what we may do with a CUDA kernel. Continuations are this idea for the completion of callbacks. So this is similar. And ownership passing was the fact of instead of sending messages, sending their pointer, which is something achievable naturally in shared memory, but it was not retained because of the data type support. So overall, in this world of MPI in shared memory, so MPI to address complex parallel hardware, patterns of interest, in our opinion, are the remote procedure calls, because they allow to have MPI acting as a coordinator between, of course, other programming model, and maybe shared memory queues, even if it is what we observe in the HPC field. Languages are eating a lot of the runtime support, and such queues like in Go or possibly in Cocos also may appear as a way to communicate in shared memory. On the runtime side, because we were speaking of the MPI support, but there are already several runtimes and approaches proposing to run MPI processes in something else than Unix processes. User level side, there is hybrid MPI, adaptive MPI running in threads, process in process, which uses DLM open to map processes also in shared address space, and eventually also MPC, which is the runtime I've been working for the last 10 years, which maps, as I will further describe in a few slides, MPI processes in threads. There are also, and it's worth mentioning, kernel-level approaches such as SmartMap and PVAS. But let's now focus on MPC. And so what is MPC? MPC, it's an MPI implementation, which runs on user-level threads. And so it is a thread-based MPI. In this case, when you launch your parallel application, you will naturally launch Unix processes, but these processes will not be MPI processes anymore. So what is going to happen is that we will have a PMI rank given by Slurm or whatever launcher you have, which is different from the MPI process rank, which is on the top of this figure here. Inside MPC, we can run either on pthreads, so running MPI ranks over threads, or, and this is the default case, over user level threads, which could be called also coroutines. And in these coroutines, you may have user level threads, which are these MPI processes at the end of the stack. So this gives us a new freedom degree that we don't have naturally using process-based MPI. And of course, this brings also a lot of issues. And the kind of issue it brings is how do you translate a code which exists, for example, on the left, a very simple code with a global variable, to threads. You naturally see that if you run your process, which has four, if we look at the top, we run in process-based, meaning we launch as many Unix processes as threads or MPI processes, no problem. The global rank is okay. Naturally, if you run all of these ranks in the same process, you will only have a single image of the program and thus a single image of rank, and they will collide and it will break your variable. So in MPC, we developed a privatization mechanism, which was a paper in EuroMPI maybe 8 years ago. It's in done, but I have a window over it. And so in this paper, we describe privatization, converting global variable to TLS. And by doing so, we are able to run existing codes inside user level threads. And what is fun looking at the past is that the title of this paper was a task container as an alternative to runtime stacking. And it was already containing this idea of horizontalization as profitable for parallel runtimes. So this is what MPC does to run, and this allows us to launch MPI processes in various configurations. So here you have the process-based case, meaning one Unix process per MPI process. So it's a lot of MPI process, such as in MPC, we call them MPI task or tasks, not to make the mistake of what is process, but other story. So here we have the equal number. Of course, we can run a single Unix process for multiple MPI processes, so one process per node. And we can do a mix of both. Two process, so one per NOMA and MPI task inside. So this was a bit of the framework of the discussion I made before about horizontalization, because we're working in such environment where we have freedom and MPI processes give you some idea on what you could achieve for horizontalization and also for malleability. Another aspect which is important, as I will outline what is needed to have this in session, is the launching capability. So let me give me a few minutes to describe how we launch MPC. Of course, we rely on the PMI. So when we have Slurm spawning our processes, we will have regular Unix processes. Each of them will be attributed a PMI rank by the batch manager. But we overlaid over these processes an overlay network. And so again, it's a publication from 2 years ago. And developing this overlay network, the idea was to allow full connectivity on a supercomputer, including between jobs. So this is what you see on the right. The balls, I could say, are the overlay network, which uses a Kademlia topology. And the prism between them is simply the connection between the root of each of these jobs to be able to do the process discovery. Because discovery is important if you consider a client-server world, because MPI is not only mapping, it's also interacting / discovering these new processes. So this overlay network acts as a backplane to exchange connection information, so just the PKeys and such to when you establish the connection over your networks. But it also allows to number processes in a unique manner. And to do so, we rely on a set ID. Set ID is simply the job ID concatenated with the user ID. And also each process in this set will have a unique ID, which will now be used in a replacement of the world rank. This allows us to address all the processes participating in the jobs on the machine in a unique manner. And on top of this, naturally, for each job, we have the MPI rank that we can now decouple from the process, from the Unix process, because in MPC, we need it as with run in thread. But as I will further describe in one slide, we would like to do the same using sessions. And so sessions at the rescue, the problem is the following. MPI has been working on hardware topology because, as we have seen, hardware topology is becoming complex, and so MPI also needs to look at it. However, now we have split, so very advanced split, to be able to address hardware, but sadly, they can only work on Unix processes. So this is what I show here. We have two NUMA, and let's say we want to split on the NUMA. We do hardware topology split on these MPI ranks, and we end up with two communicators, each addressing a NUMA. Very well, except that the granularity of this split is Unix processes, with the drawback I previously shown that Unix processes are less tightly bound than, of course, shared memory, where you can directly address data. So imagine now we want to split on a single process. MPI does not propose us the ranking abstraction to do so, because the Unix process has its rank if we consider the direct correspondence between a Unix process and an MPI process. However, we consider a possibility using the session model. And in the session model, we could imagine a topological split, but it also has a lot of side effect. So imagine we want to split on a NUMA. We could create MPI ranks, which are part of the same process, and use the context inheritance supposed by session to manipulate different rank, because they would have different communicator. And even to get your rank, you need to pass a communicator. And as such, you would end up with virtual ranks, which are exactly endpoints that were described previously. And I'm still convinced that such ranks could be helpful to address more complex hardware, as I've described for GPU. And in fact, this is exactly what the collective communication libraries for GPUs are looking at. And such, I think I have one more slide. And this slide is more about how it could be done. So imagine we start from a P set, so sessions, for those who may not be comfortable about it, but I'm sure most of you are, it's just the idea of creating a group from a process set, which has an URI descriptor. And from this group, you can use a sort of collective call in the sense that all the communicator members must participate in to build the communicator. So it's a bit of a magic call in MPI. So this call is MPI com create from group. Now imagine we want to create endpoints or similar ideas to endpoint with it. We could use a P set which would have a number in it. So we would create two endpoints over world. So syntax is to be discussed, but the idea is we want to have two endpoints inside each process from world. So here you can just get a group, but this group would have the specificity that it has some ranks inside which are not from world, which is something strange. Most MPI runtime rely on the world rank in the group. In MPC, thanks to the work about the overlay network, we now have the UIDs inside the group, giving us a freedom degree on this aspect. So there is a possibility to create ranks at this step. And the second part is the collective nature of the MPI com create from group. It means that all the participants need to participate in it because it is collective, building a communicator. However, in the case of virtual endpoints, they may not be bound to an executor, meaning that you don't have the threads which will run. You just want to create endpoints that you may distribute to your CUDA kernel / other threads that will come in the future. So we may need a com endpoint from group, which is exactly the endpoint proposal, except that it does not work on the communicator, but on the group, to create such endpoints from a session. And why this? It is simply that it would allow to explore MPI in shared memory, but doing so this is only the building part of the endpoints, but doing so also may need some new synchronization and ability to coordinate more than communicate, because in shared memory, you don't have much of the problem of moving data like in distributed address space, but more of knowing if something has finished and starting a remote thing. So the continuation and the RPC are more interesting pattern in this layout. Looking at the job as horizontal, so and software differentiation, which are the topic I described. So it's a relatively high-level talk. Sorry, I'm not sorry for such, but I think it was important to be able to defend the notion of MPI ranks, which are not necessarily MPI processes, which are not necessarily Unix processes. And with this, I'm done, and I will be happy to answer all your questions. Thank you.
So we have time for one, maximum 2 questions in the room. Yeah, let's go.
So thanks, Jean-Baptiste. I was looking at this, and I'm thinking of the codes that I've written where the optimal placement of threads and in terms of NUMA and everything else is actually fluid across the entire workflow. So some things would be useful to have communicators or MPI ranks being close, far, and it's just easy enough to create various communicators as I go along and then discard them as I see fit. Because the optimal position of processes versus in terms of cache coherency varies across the workflow. So some things would be cache coherent, other things are truly independent. And I'm wondering, would this ease that? I mean, when I'm looking at this, I'm thinking of writing codes. I basically have to start my workflow with some sort of appropriate distribution of MPI across the various NUMA nodes and sockets and MPI. And then knowing that, say also make sure you have all these communicators that you're going to use across the entire workflow. These are going to be this size, this size, this size, with this type of arrangement. It's a bit tricky to handle. Are you proposing this as maybe an easier way to do it? Because right now you could do communicators with a ton of this stuff, right? But I feel like I'm missing something. So how would this make this easier? Would it?
It would make things easier because most of the programming models, I would say, OpenMP and CUDA, are operating on threads or locality inside a given Unix process. And MPI is between Unix processes. Yet MPI has a lot of support to compute mappings or complex mapping in terms of topology using the hardware split. Of course, you put the point on one of the aspects is that yes, you will get a communicator object, and more than this communicator will not be bound to an executor, because we know the executor is what is having the CPU set or the locality, which is important. You're right. So indeed, if you spawn in a thread and you have the CPU set of the thread, if you spawn in a process, you have the CPU set of the process. If you spawn on a GPU, you will have the locality in the GPU. Yet, in terms of coordination, and this is what I was outlining in this slide previously, I think it has a lot of merit to have a single index. Because if you do triple nesting, MPI plus 6 plus Y, we suffer from this indexing because we need to map the data recursively towards the GPU. And at the end, we don't know what is on the GPU and what is not on the GPU. So, because you need to split a lot and piecewise in a very impressionist manner. And so this is where the merit lies. I agree. In launching, there might be more complexities, but doing it with a single abstraction can be helpful because you would have a single address to speak to the individual pieces of your split. I don't know if it's clear, but particularly in using CUDA, which has a very high-dimensional split potentially. You could do one linear split and then have each of the components working on their piece. So this is the main benefit I see for programmability. But you're right, purely launch side, there are still missing pieces to say to OpenMP, this is your CPU set. To say to CUDA, this is where you run. There is a lot of glue needed here, yes.
Okay. Thanks a lot.